Good morning. Let's have a class. And we'll move on to the lecture 4 of the AEM 341, exam 1. And we'll have this week, Tuesday, Thursday, over the weekend, I'll put on the eCampus of a practice exam. And the next week, Tuesday, we'll do the review of the exam 1. And Thursday, we'll have our exam 1. Okay, so that will be the plan. So let's talk about this lecture 4. We'll talk about the microbial growth and the nutrition. We basically talk about the microbial growth today. So first of all, this is very important, you need to know. Bacteria growing, or we can say microorganism growing, is binary fission. And this is already being shown you on the picture. So what happened? You have a microorganism. They were going through a DNA replication, and there is a cell wall will be generated and separate them. And in their new daughter cell, they will be generate an exact same DNA sequencing, and finally they separate. So this is basically is 1 becomes 2, 2 becomes 4. 4 becomes 8, 8 becomes 16, so we say it is 2 times the power of n. That's called the binary fission. Now, theoretically, the daughter cells should carry on the exact same genetic information from their mother cells, but we know they're going to have something change. It is same thing like you looks like your parents, but not exactly the same. Because we say it is mutation. It happens in the animals and the human beings. It happens also will be in the bacteria. Okay, so that's something we know. Now, the second thing is the generation time. Generation time. Generation time, said very simple, is we can understand it is equals the doubling time. Which means how quick the 1 will become 2, 2 become 4, 4 become 8. And we already mentioned, for some of the bacteria, the generation time is very short. Let's say E. coli. The generation time is only 18 to 20 minutes. So that is the reason. For E. coli, even you have 1 cell, you grow at 35 degrees Celsius, 24 hours. It will become basically 10 to the power of 8 cells per ml. So very density. Because the generation time for E. coli is only 18 to 20 minutes. However, for Microbial tuberculosis, the doubling time is very long. That's 12 to 24 hours. This is the reason. If we have a patient got tuberculosis, you cannot wait to get a sputum sample, get isolated the microbacterial tuberculosis, then to do the treatments. Because that's going to be a couple of days, could be a couple of weeks. That's the reason the microbacterial tuberculosis, we need to rely on a very important clinical testing staining technology, which is we call it acid-fast stain. Because if acid-fast staining positive, we can say this patient is presumptive TB positive. So we have to use antibiotics immediately. Okay, so this is the slide tells you why microbacterial tuberculosis cannot wait until we get a single colony. The reason is that the generation time, the doubling time is very long. It is extremely long. And E. coli is very quick. Okay, this looks like a little bit complicated, the math behind it, but there is something I want to explain to you, and we're going to talk about that. Bacteria, because for most of them, grow dramatically, especially at 35, 24 hours. For example, E. coli, Salmonella, Listeria. So for bacteria, we do not count just like that. Okay, we don't say 100,000 cells. We don't say, like say, 250,000 like that. This is too long. And if imagine if you are doing a research, you have one group of the bacteria. Okay, you get 20, 30, 100, 1,000, and 10,000. And you have another group of bacteria, get something like that. Okay, you get something like this, and 5,000. Now, can we do a statistical comparison between these two groups? Obviously not, because the error is too large. So what we have to do, we need to change them into log 10 cells per ml. So that's a little bit about the mass. Log 10, 10 equals 1. Is that right? You know that because 10 to the power of 1 equals 10. So log 10, 100 equals 2. Because 10 times the power of 2 equals 100. For example, log 10, 10 to the 8th equals 8. That's what we do for numeration bacteria. We're using log. Because all these things change to log. It all becomes single digits. And this problem we solve. So that's why from the static standpoint, we don't record the bacteria original number. But there is one exception we want to mention. For example, E. coli 0157H7 in ground beef. And this is based on USDA, United States Department of Agriculture, Food Safety Inspection Service. This is zero tolerance, which means you cannot have one cell there. At this moment, we cannot do the log calculation. That has to be a log data. Okay, because that's a strict regulation. But other than that, in the lab, we basically change them to the log. Now, this is a slide which is basically we talk about the mass, how we measuring the generation time. So what they do is that they assume NT equals N0 multiple 10 to the N. Okay, so you can see what it looks like. This NT, this is the population at the time T. N0, this is original population. This guy is actually the number. Okay, how many generation number? So when you have this formula, we're going to change them to the log. So we put the log 10 there, we put the log 10 there. Then you need to know a little bit of mass. This equals log 10 NT equals log 10 N0. And then we do it. This goes to log 10 NT equals log 10 N0 add N log 10 2. And then we also can do a little bit of transformation. This N equals log 10 NT minus log 10 N0 and divided by log 10 2. And we know log 10 2 equals what? 0.301. And then this is a generation number. If we put a t here, we put a t here, this is the time. And this is time, which means how many times has been 60 seconds, 100 minutes, 2 hours. Now, this is a general formula. If we want to only talk about one specific number, let's assume this is only one generation comes out. So what is this going to be? Then this is become G, generation. So the top will become log 10, 2, and 0 minus log 10, N0, and the bottom is what? 0.31 and G. And so this guy could become log 10 2 and log 10 N0 minus log 10 N0 and divided by 0.301 G. And this is gone, this is gone, this is the same thing right here. So what happened? This here NP equals 1 divided by G. And this is what? This is growth rate. And growth rate, we also could use a constant of T. So that's why T equals 1 divided by G. So in other words, the conclusion, the growth rate is a reciprocal number of generation time. So that is the conclusion. Even if you don't know about these maths or you're not good at maths, it's very simple. You need to know the conclusion. The generation time is a reciprocal number of the growth rate. Okay? So that's what we have here. But this is just a math. We just need to know what it comes out. There is a certain software has been generated with the new machine learning AI technology. That's another topic, which is called predictive microbiology. But here, this slide, which is really nice, gave you some of the hints and some of the introduction, what are those maths comes from. Okay, it's a log-based calculation. So just want to let you know, but you only know here is the conclusion. You don't need to worry about all these calculations, how they get. But the key thing here, everybody should know, is a bacterial growth curve. This is important, you should know. Okay, a bacterial growth curve, the y-axis and the x-axis. The x-axis is always time, and the y-axis is the population. Usually is log 10 colony forming unit per mm, or log 10 cell per mm. Now, to keep in mind, the bacteria grow. Let's say a bacteria grow in the broth at 35 degrees Celsius. Let's say we have a bacteria grow at 35 degrees Celsius, 24 hours. It's not grow linear. It's not grow like this. This is linear. It's very simple. You think about it's all just like the more time it will be grow more. Actually, it's not. What's a curve looks like? It's really curved, have a different stage. It will be not like this, because it's not going to grow immediately. It actually will have like that, very flat, very steep, flat again, and go down. So that's a typical bacterial growth curve. We have 4 sections, so basically I have 4 segments. This is a lag phase. Okay, the lag phase is very easy to understand. When bacteria in a new environment, they have to accommodate for different conditions, especially in the real life. So they have to do a preparation. We can say this is genetic preparation for growth. That's why it takes time, called a lag phase. Once the bacteria has accustomed to the environments, they're going to start to grow dramatically. And 1 become 2, 2 become 4, 4 become 8. And that is called log phase. It usually grows dramatically. So there is a certain period of time, the curve is very steep. And we know that during the bacterial growing, they will generate toxication materials. And they will use the nutrition of the medium or from the environments. So the toxication material are going to build up and the nutrition going to use up. They will reach a balance. And by the time the dead cell and the live cell is similar. So we call this is going to stationary phase. And later on what happened? Because the toxication material from metabolic process is started to accumulate. And one of the example you need to know, if you have a bacteria broth, let's say we grow E. coli at 35 degrees Celsius, 24 hours. You know what will happen? Originally, the broth pH is around 6 to 7. After you grow 24 hours, that pH will go down 3 to 4. So the acid is one of the metabolic products will killing the bacteria. So later on, because metabolic products, the toxication material is accumulated, and more than the available nutrition you still can use, so the numbers start to decline. And this is become death phase. Okay, so that's very easy for a bacteria curve. Now there is something we want to mention. We will mention again, but we want to talk about here, let you understand it. You heard about, there is two things we always talk. Number one, we say killing bacteria, which means bacteria is killed. Number two, we say inhibit bacteria, which means the bacteria is still there, but don't let them grow dramatically. The killing bacteria, a good example is we using antibiotics. For example, you have ammonia. We're going to using penicillin or amoxicillin. We have to kill Streptococcus pneumoniae. So we have to kill bacteria. Inhibitor bacteria basically is antimicrobials they're using in a food processing because we want to extend the shelf lifetime. So what's the difference if we want to use a curve to express? Killing bacteria, basically like this. That is a killing bacteria. They did not even started at log phase. The numbers start to decline. But what means inhibit? Inhibit, which means the lag phase time is extended. However, eventually they're still gonna grow. Okay, this is something I want to tell you. That's called inhibitor bacteria. Basically, extending lag phase time. Okay, that's a very important concept. We want to let you know. Now, obviously, the log phase, because it's growth, which is 2 times the power of m, so we also call it expositional time, expositional phase. Good. Two things we want to mention very briefly. First of all, same as a human being and animal cell, bacteria dead is a programmed cell death. So there is an internal programming for them to die. Obviously, if during this process there is some mutation happens for animal and human being will cause to cancer. Is that right? That's a programming death. Second thing is really bothers the food industry a lot is called viable but non-culturable, which means the bacteria use traditional cultivation methods on the agars, in the plates, in the agar, in the broth on the agars, they cannot grow. However, the toxication material is still there. So we call it a viable but non-culturable. So the idea is that for these methods, we cannot use traditional bacterial analysis methods. We need to rely on modern technology like molecular methods, like 16S RNA, to testing their toxication. So these are the two things we just want to make sure you understand in very briefly. Is there is two kind of alternative hypothesis for the bacteria to die. It could be viable but non-culturable. It could be programmed death, cell death. Okay, very quick. So the major topic here we want to talk about is factors affect microorganism growth. We will mention 4 major impacts, which is pH, temperature, water activity, and oxygen. Among those 4 factors, pH and temperature relatively is easy to understand. Water activity is most tricky one, and oxygen concentration, we have some topic we could talk about that. So, we're going to remove all these. We're going to talk about these single factors related to the bacteria grow one by one at each time. Okay, something is related to the chemistry, physics a little bit. So it's a comprehensive system. You can understanding about these materials. So first thing first is pH. This is the one everybody knows. In your high school, you already know what is pH. Okay, pH calculated equals minus log 10, the concentration of proton, or we say hydrogen plus. And the range of the pH in a solution, which is a range from basically 0 to 14. And at 7, we usually call it a neutral. It's a neutral pH. At 14, we call it a very alkaline. At 0 to 1, we say it's very acid. So the first question is very simple. Which material is pH close to 0? That is a very important common sense life question. Battery acid. This is the reason the battery has to be doing recycle. Ideally, you shouldn't throw away in the general trash can because it's very corrosive. Which is the pH is 14. That's 1 mole sodium hydroxide. Okay? It's a very simple knowledge. Now for the bacteria medium, when we make, usually we like to keep neutral, but not exactly neutral, usually 6.5 to 7.2. In order to do that, most of the bacterial solution have phosphate buffering ingredients. Because we want to make sure the nutrient pH. That's most of the bacteria will love, so we call it optimal growth. Generally speaking, when the pH less than 4.0, which means goes here, the bacteria will be dead, or we can say it's killing bacteria. A very easy example. We had something pH around 1 to 2 is stomach acid. So that's why stomach acid is part of the first physical defense system of your body. Any bacteria go to cause pathogenic impacts have to passing through the stomach acids environment first. So basically, there is a research has been done, have the conclusions there. If it's around 4 to 5, we say acid environment, only yeast and molds can grow, most of the bacteria cannot grow. Therefore, we could classify the bacteria based on the pH into acidophile, neutrophile, and alkalinophile. Alkalinophile. Okay. We listed the pH there. it's not really strict. So we say 0 to 5.5 basically is for fungi. 5.5 to 8.0, most of the bacteria. And there are some bacteria is like alkaline environments, is Bacillus, Micrococcus, and Pseudomonas. But it's not really strict. So for example, E. coli at pH 4 and 5, they still can survive. It won't be kill everything, okay? So just want to let you know. So I don't want to be mentioned about the range here because it's not really strict. Now something else we want to mention. In the bacteria medium, because we want to see whether bacteria generate acid or alkaline material, we lots of the time using pH indicator. A very important pH indicator we are using is called phenol red. Because the phenol red at alkaline environments it is cherry red, and as acid environments it is yellow. So lots of the time we're using these ingredients to determine whether bacteria has been generated the acid or in the other direction in the alkaline environments. We will mention this again in the lab section and when we talk about the medium. So bacteria doesn't like really acid environments. So once the acid environments generate what they do, they will pumping the acid out. And lots of the times they also will be exchanged with potassium. Now this is cause another problem, which is in the food industry, it's actually hurt a lot. So for example, I have a beef. I have a beef chunk, let's just say. What are we going to do? In order to prevent a microorganism, especially we have a zero tolerance for E. coli 015CH7. So I will spray antimicrobials. So for example, I'm spraying lactic acids. Okay, but you need to know when we spray lactic acid, it's not going to kill everything. Because the process we call it sanitizing. It's only reduce the microbial organism to a certain level. So what happened? More or less, you have some residual bacteria. Then the residual bacteria will become acid resistant. And once the acid resistance generates, they will generate cross protection impacts. Which means you may need a higher temperature during the further cooking process to kill the bacteria. But what it will generate? The higher temperature will damage the palatability of the beef, because the beef we talk about is juiciness, tenderness, and the flavor. If you're using too high a temperature to cook, you may be killing the bacteria, but certainly will hurt the tenderness. Is that right? That's the reason. So just want to let you know there is a problem generated. So once the problem generates, what the industry they do, in order to prevent the acid resistance, they need to prepare at least 2 or 3 different types of antimicrobials and do the rotations. So you have alternative chemicals to the preparation will let the bacteria can survive the acid but cannot survive maybe the other environments. So just want to let you know this is something happened called acid resistance. It's very severe in the food industry, especially the meat industry. Okay, so this is the pH impact. Temperature, the second one. This is the first one, the pH. Temperature is very easy to understand, to be honest, because temperature is connected to the enzyme function. So very easy understanding, when you have a fever, you will feel very drowsy, lower energy, and even you eat, you lose appetite lots of time. Because the enzyme in your body is not working, and for the bacteria it's the same thing. So for every bacteria, the temperature is correlated to their functionality of the enzyme. So they always have a minimal, optimal, and the maximal range of the temperatures they can grow. Now, based on this, we could categorize them into different categories. This is a picture showing you what's happened. The x-axis is the temperature using degrees Celsius, y-axis is the growth rate. And you can see they're curved. They always have an optimal temperature right in the middle. And this is the one which is tell you the range. So there is a five basic range or category based on the temperature requirements. Let's talk about something first. It's called a mesophile. I wanted to start from the middle. This is 20 to 45 degrees Celsius. Majority of our foodborne pathogen, all the bacteria used in the lab is mesophile. That's the reason we grow 35 degrees Celsius always. But keep in mind, they can grow as high as 45 degrees Celsius. They give you a tricky, which means using mild heat, not only curing them, maybe let them grow dramatically. So at 35 degrees Celsius, they may need to take 18 hours to grow to 10 to the 8 cells. If you grow them 42 degrees Celsius, maybe only 9 hours can reach that number. This is one of the enrichment used widely in the food industry to rapidly testing bacteria. That's called enrichment. So the first category, lots of people will be using is mesophile. We will talk about this mesophile. Okay, the second category, cyclotroph. This is usually 0 to 20 degrees Celsius, or even 30 degrees Celsius, 35 degrees Celsius. Okay, this will give us a trouble. Why there's a trouble will generate? When your bacteria have the range of 0 to 35, which means the bacteria can grow in the refrigerator. This gives you trouble. Because when you buy a food products, you always will do the first thing is put in the refrigerator. Then you think it's safe for a couple of days. However, there's some more bacteria will grow. And which bacteria is very important, categorized as cyclotrophs, Listeria monocytogenes. And this gives United States food industry a big problem back 10 years ago. The reason is they can grow at refrigerator temperature. So, hot dogs, ham, turkey breast, all those daily meats, or we say ready to eat meat, it's a big risk. Even we do a vacuum package, they still can survive because they can grow in the refrigerator temperature. Okay? Now, there is some of the bacteria can grow in a very extreme cold condition. We call it the cyclophiles. That's 0 to 20 degrees Celsius. I will say they can grow in Antarctic and the deep ocean marine area. This is environmental bacteria. And the scientific area are very important about these bacteria because in those extremely cold conditions, they definitely have some enzyme from them, have a specific or typical or special biological function. So that's lots of people are doing those things. But it's an environmental microorganism. So we go back here, cyclophile, cyclotroph, and mesophile. Absolutely, there is some bacteria which is resistant to the heat, called thermophile. Which bacteria? We already did. Bacillus. They can survive as high as 55 to 85 degrees Celsius. A good example is bacillus. Now there's a last category. because the hyperthermal files, where you can see those bacteria. In the United States, you can see them in Yellowstone National Park, in the hot springs. They can grow in the range is 85 to 113 degrees Celsius. Why this is also important? We have some environmental microorganisms, like hot springs, you can find them. They have a specific enzyme. Okay? We can use. But more important, we can use those bacteria to testing whether our autoclave is working. Our autoclave temperature, the one at our room close to our microbial lab, is 121 degrees Celsius. They can survive up to 113. So, whether the autoclave is working or not, we put the bacteria there. If it's dead, which means our autoclave is working. Which bacteria? Geobacillus. Another thing, very important from hyperthermal files. Some of you work with some professor in the health science center. You do PCR all the time. Is that right? Some of the people. There is one enzyme you're going to use is called TAC enzyme. The TAC enzyme can survive in at least 94 degrees Celsius, a very high temperature. Where they come from? They isolated from some special bacillus, or sometimes from geobacillus. So all these thermophile, hyperthermophile, they could do a quality control for our autoclave. They also could using for our molecular microbiology technique tool as one of the tools, especially the TAC enzyme. Okay, so just give you an example. So that's a temperature range for cyclophiles, cyclotrophs, thermophiles, hyperthermophiles. Okay, we're going to move on to water activity. This is one of the relatively difficult material. We need to explain to you what this means. This is called water activity. Okay, first of all, water activity is not moisture content. I have a graduate student a long time ago. When I asked her a question, I said, what is water activity? She doesn't even think. She tells me that means the amount of the water. No, that's a wrong concept. The amount of the water equals moisture content. Now, what is activity then? Then what is water activity? Water activity equals partial vapor pressure above a solvent, okay? Let's just say a solution or a subject, and a partial divided by partial vapor pressure of pure water. And the bottom is always equal 1.000. So above is must less than 1.00. So the number value of water activity is always 0 to 1.000. Like that. Okay, now what this means. This gives you some trouble to understand. Okay, we have to explain to you what happened. So this is going to be some chemistry, some physics, mixed stuff. What is a partial vapor pressure of pure water? Or we say above pure water. So I have a closed vessel like this. Okay, let me just draw a little bit more, a little bit large. I have a closed vessel like that. I put water there. Okay, H2O right here, H2O right here, H2O right here. Now what it looks like? You remember this? That's water molecular. Oxygen, hydrogen, this angle, 109 degree. This is called tetrahedral arrangement. And they also call sp3 tetrahedral arrangements. We're not going to go that deep, okay? What are the bonds between O and H? Covalent bonds. Okay, you can connect it to another H right here, is that right? This is hydrogen bonds. And we can't talk about distance, we just forget about it. Okay, basically it looks like that. Well, when we have a water in there, what will happen? Some of the molecule of water will go out of the surface. Some of the water molecule will come back. So at the end of the day, they will reach a balance, which means the molecular water flee away and the molecular water back to the liquid phase, they're going to reach a balance. And what will happen? They will generate a pressure like here. Okay, all we can say, we use the opposite direction. It will generate something like this. This is called partial vapor pressure. And we also should know the partial vapor pressure will increase with the increasing temperature. So, for example, if I have a fire here, I'm heated, let's say. I'm doing the heating. What will happen? The partial vapor pressure will be increased. And when the partial vapor pressure equals the atmosphere pressure, which equals 1.05 times to the 5 Pascal, what will happen? It's a very simple physics question. If the partial vapor pressure above the pure water increased with the heating equals the atmosphere temperature and atmosphere pressure, what will happen? The boiling will happen. Is that right? And then it comes out another question, which is the boiling temperature. What's the boiling temperature? The curve will look like. It's related to, this is boiling temperature. This is the elevation. It is opposite direction. Is that right? Sorry, not this one. It is opposite direction where it looks like here. If its elevation is 0, this will be 100. Sorry, it should go opposite direction. So, if you have a boiling temperature right here, this is the elevation. What's the curve looks like? So, curve looks like this way. At 100 degrees Celsius, usually, the sea level elevation at West Virginia, let's say we have an Appalachian Mountain. So, what are our boiling temperature? I tested at 94.5 degrees Celsius. If you go Rocky Mountain National Park at Colorado, the boiling temperature is basically 92 degrees Celsius. If you go Himalaya at Nepal, what are we going to do? It's like 70 degrees Celsius. So what happens if you put an egg there at 70 degrees Celsius, it starts to tumbling. But can you eat it? Of course not. Because it's really boring, but it's not really heat enough. So it's not going to kill the bacteria. The protein will not agglutinated there. Okay, so this is the partial vapor pressure, what this means. Now, once you have a solvents, what will happen? So let's just draw another picture. Let's say in the solvents, similar as in our food products, I have a salt, I have a sugar, and I have protein, all those small molecules to macromolecules. And then I also have a water there. Then what happens? These chemicals, they were dragging down the water. So compared to the pure water, the water free away is much less. Therefore, the partial vapor pressure in a food products or in a solvents is much smaller than in the pure water or above the pure water. Because the sodium chloride, the protein and the sugar, they were dragging them down. This is a reason why in a food products, the water activity is always a little bit lower than pure water. So for example, at a hot dog, we say the water activity is 0.995. How about beef jerky? That product is a little bit dry. This is about 0.911. Okay, how about the dry food like crispy, like chips? That's very low. Chips, the water activity, 0.250. So that's water activity. That's what it means, a partial vapor pressure. Now, we go back to the older question. What it means moisture content? That means the amount of the water in the food products. What it means water activity? It's a partial vapor pressure above the food and a partial vapor pressure of pure water. Now, what's the connection between that? This is related to another interesting curve. We want to talk to you about that. If I have a x-axis and a y-axis, the x-axis is water activity. Y-axis is equilibrium moisture content, which means the balance of the moisture content. Then I have a food products. I will do let the food to absorb to water and desorption to water. What's the curve will be looks like? The curve basically looks like this. Which means the absorption and desorption of the water in a food products is not reversible. But we want it to be reversible, is that correct? So think about it. If I have a beef product, when I don't want it, I got dragging out all the water. When I used it, I put all the water back. That's a really nice technology because food safety will never be a problem because when we're dragging out all the water, the bacteria will be dying. And when we need it, we just put them back, assuming they don't affect the quality. But is that going to work? Of course not. Because absorption and desorption is not reversible. Now, based on this, every food products could have three categories. This is a value just, okay, we'll just tell you very simple. In this category, the water is from mono layer. What are the foods right here? Chips. So chips, the water activity and the moisture amount is very low. So water activity is very low. which means available water for bacteria to use is very limited. So did you ever heard about there is a foodborne outbreaks on chips? You never heard about that. Is that right? You never heard about it. In the second category, this is what we call it additional layer. In the additional layer, what will happen? What are the food products? Is chewy chocolate ball. You like that? You have a party to watch the football game, you have a chewy chocolate ball. Did we ever heard about the chewy chocolate ball have outbreaks of foodborne pathogen? You never heard about that. But what we heard about that is always beef, fresh produce, because at this curve, at this range, this is capillary water, and at this range, the water activity and the moisture amount is highly correlated. This is the category is fresh produce and beef products, chicken. We care about is foodborne pathogen. Now go back to see some additional question. What we care about for the chips? If you open a bag of chips, you put on your bench at the dawn for a week, you go back to taste it. It's become sweet or it's become rancidity. We care about is lipids oxidation. Is that right? We care about lipids oxidation. Okay, in the second category, chewy chocolate bar, what we care about? We want the beautiful chocolate color. Where that comes from? That comes from Maillard reaction. That's a chemistry, completely chemistry, okay? So we don't talk about these in this class. We more care about, in our exam 4, is for chicken, fresh produce. That's what we care about is foodborne pathogen and harmful bacteria. So that's the reason we want to explain to you the whole story, what is water activity. So, what this means for water activity? That means available amount of the water the bacteria could use. Now, what is the moisture content? Amount of the water. Are they correlated? Yes, but they're not simply the same. And always remember, absorption, desorption of the water in the foods is not reversible. Okay? Now, water activity, based on water activity, we could simply categorize bacteria into two major categories. Is based on whether they are using certain amount of the sodium chloride, is halophiles and extreme halophiles. So halophiles is optimal 0.2 mole and extreme halophile is 2 mole. What is halophiles? There is one bacteria we mentioned a couple of times. It is widely existing on our skin surface. Because when you go into jogging about 2 miles, 5 miles, you're going to sweating. What's going to generate is salt. There's one bacteria favors that environment, which is Staphylococcus aureus. So Staphylococcus aureus is a halophile. Now where are you going to see the extreme halophile? In Great Salt Lake National Park, State Park in Utah, in Salt Lake City. When you go there, you will see most of the environmental bacteria are extreme halophiles because the Great Salt Lake selected those stuff. Okay? So that's very important, is effects of sodium chloride on the microbial growth. Okay, the next one is also a little bit tricky, a little bit important we want to talk about, is the amount of the oxygen to affect bacterial growth. So this is something we could explain to you in a little bit, spending a little bit of time to talk more detail about this one. Okay, this is relatively simple, not that difficult, but we need to have some space here. Look at the slides here. There are 5 categories. Looks like it's very complicated, it's confusing you. But we could simply 5, 3, major categories based on the oxygen requirements. Number one, aerobic bacteria. Number three, anaerobic bacteria. Let's talk about those two first. There are some of the bacteria must use oxygen to grow. Or we can say must be in the presence of oxygen. They can grow. For example, Pseudomonas. A very widely used bacteria is Pseudomonas aeruginosa, or Pseudomonas fluorescens will generate fluorescence color, natural fluorescence color. That's an aerobic bacteria, must use oxygen. There is another category of the bacteria cannot survive in the absence of oxygen. In the presence of oxygen, in the presence. That means the bacteria has to be survive or grow in the environment, no oxygen. Which one? Clostridium. They don't like oxygen. You have 0.1% of oxygen, they're going to die. But the majority of our bacteria, we call facultative. What does it indicate? They can grow with or without oxygen, but grow better with oxygen. Most of our bacteria in the lab, or we say most of the foodborne pathogen, E. coli, O157H7, Salmonella, Listeria, Shigella, these are facultative bacteria. Okay? Now there is a question. Why some bacteria have to be using oxygen? Why some of the bacteria cannot survive in the presence of oxygen? This is, we're going to talk a little bit about bacteria electron transport chain. So you have NADH goes to FAD. We're going to talk about this later on. Okay, FES, FMN, then go to coenzyme Q, go to cytochroma C, then go to cytochroma A, then go to cytochroma A3, and finally goes to oxygen. This is called the electron transport chain. A very typical electron transport chain. Okay? Bacteria need the electron transport chain to generate energy. ATP, what they use. We'll talk about it in the exam 3. However, during this electron transport chain, they will generate toxic material. What is that? Could be hydrogen peroxide. Could be superoxygen. Or we write this. Okay, when these two generate, what are we going to do? We need an enzyme to hydrolyze them. This is need a catalyst. Hydrogen peroxide will become water and oxygen. This comes out very important test called the catalyst test. We will do in the lab. How about this guy? We need SOD. Super oxidase das mutase. Then we'll generate oxygen and release one electron. And this is important because this guy, if you don't have a catalyst, This guy will certainly generate this one. Free hydroxy radical. What is this one for? Lipids oxidation. And they could do a self-lipids oxidation by a bacterial cell. Remember where bacteria has lipids. Phospholipids in their cell wall structure, fluid mosaic model for gram-negative bacteria lipopolysaccharides. Is that correct? So that can explain very well why some bacteria must use oxygen or can survive in the presence of oxygen. Because they have catalase and SOD. Why some of the bacteria cannot survive in the presence of oxygen? Because they don't have this guy and they don't have this guy. And oxygen for them is a toxication because the carcinogenic toxication material will generate. They cannot remove. Some bacteria right in the middle, we call it a facultative. Okay, now we can go ahead to talk about the other two categories. One is allotolerant. Somehow here, there is something called allotolerant. What is allotolerant? Facultative. We say grow with or without oxygen, but grow with better with oxygen. Allotolerant, E. coli, good. E. coli is same. With oxygen, they're the same. So as called allotolerant. We talk about anaerobic bacteria, which means they don't like oxygen. But some of the bacteria, this is the category number 3, this is called category number 4, this is category number 5. Some of the bacteria can survive in a limited amount of oxygen, somehow 2 to 10%. This is called a microaerophilic. There is one special pathogen, an important pathogen is belonging to microaerophilic. Capillobacter. This is the reason Capillobacter is a number 2 foodborne pathogen in the poultry industry. But it's very difficult to grow. It's a fastidious bacteria. You cannot grow in the nutrient broth. It will not grow. You cannot grow just on the open bench because the oxygen amount is too huge. So what we need this special jar. This is a jar and the chamber using for anaerobic microbes. The left one, relatively expensive, $25,000 for the chamber. There is a pipeline connected to the oxygen and the carbon dioxide has to control it. On the right side is a lab used. It's not really very cheap, it's like $500. For microaerophilic, the only difference is the gas pack is different. Strict anaerobic microbes, they will not generate any oxygen. Microaerophilic, they will let you generate 2 to 10% oxygen. So what's the story right here? I put a gas pack. I put 10 ml of water to let it be bubbling. And we want to remove the oxygen inside of this jar. What we need to remove, what we need to generate is hydrogen. So this gas pack generates hydrogen. Then the hydrogen and the oxygen, they will react to generate the water. Now we want to make sure this reaction is happened really quickly. So we have catalyst right here. We call it palladium on the top. And we also want to know whether this works, which means there is no any oxygen remaining. We need to have some indicators. The indicator is methylene blue. Or sometimes we're using another chemical called resazolene. When the methylene blue or resazolene becomes colorless, which means there is no oxygen. So the idea for this jar is very simple. We're going to generate hydrogen. Because hydrogen will react with oxygen, generate the water. Lots of the time, the jar is very humidified. And this picture is not very good because most of the time we need to put the paper towel inside to absorb the extra liquid generated. Because lots of the water going to generate, you will see it's humidity. We're not going to do the anaerobic microbials in the lab because we don't have those cross-treated. But we will do a microallophilic environment, use candle jar in the lab, which is for your throughout culture. And you will see the bacteria grow in the jar on the blood agar with a candle, and when the candle off, only like 2 to 5% of oxygen still remaining, and you will see the water, the limited amount of the moisture going to generate. And that will be our lab 11 or 12. We talk about throughout culture. Okay, so that's all we have today.